Welcome back to Physics 371 Online. This time we're going to define a new quantity that we call H, sometimes referred to in magnetostatics as the auxiliary field. And we'll use it to develop a new version of Ampere's law that's very useful in analyzing magnetic materials. So here's the scenario. We have a magnetic material that's conducting, so it can carry a current. We can hook it up to a battery or power supply, and a current can flow through it. We'll call such a current a free current, one that is due to a potential difference across the sample. But this material, if it's magnetic, can also be magnetized, and so due to its magnetization, it can also have bound currents. So for such a material, we'll write the net current J to be a sum of bound current density plus free current density. Now, we can use this to substitute into Ampere's law, which we know is del cross B equals mu naught J. So that if we put in the expression for J, we now have mu naught JB plus J free. And in our next step, we're going to the J bound, and we're going to substitute in the definition of it that we obtained when we were first analyzing the field due to a magnetized object. Remember, JB is equal to the curl of the magnetization M. So I'm going to solve for I'm going to divide both sides by mu naught, so we have 1 over mu naught times the curl of B equals, of course, just JB plus J free, but now we substitute in for J bound the curl of M. And what we see in this equation is that there are two quantities involving curls. So let's collect the two terms that have curls, and in the process we will solve for the free current density J free. So collecting the curls, we get the curl of, we can take the 1 over mu naught and put it inside because it's just a constant. So we've got the curl of 1 over mu naught B, and then subtracting del cross M from both sides, we get the curl of minus the curl of M. So this then equals J free, and you should look at this and realize, hey, that's pretty close in form to the original version of Ampere's law. There's the curl of some vector quantity which is equal to something that involves a current density. Only now what we have is the curl of the whole term in parentheses equal to the free current density. And so this motivates the definition of this auxiliary quantity that we call H. So H will define to be the term that's inside the parentheses. H is equal to 1 over mu naught B minus M. And what this allows us to do then is write a slightly different version of Ampere's law in terms of H. So the curl of H is just J free. And the reason that this is useful for magnetic materials is we have this field H that we can calculate through just a knowledge of the free current density. So all we have to know is whatever current flows through the material due to a potential difference. If we know that, then we can find this quantity H using the standard techniques of Ampere's law. And of course, when we do this, when we have some sort of free current and we want to find H from it, usually we will use the integral form. So remember, the integral form of Ampere's law in a vacuum was just integral around a closed loop of B dot dl was equal to mu naught times the enclosed current. But that enclosed current consisted of both bound currents and free currents. Here we've got an expression for the integral of H dot dl, and it's only equal to the enclosed free current density. So we'll have to use the same bag of tricks that we always have used with Ampere's law, exploiting the symmetry of the fields, because H has the same kind of symmetry that B does. So if we know something about the symmetry of H, and if it's a high enough symmetry, then we can calculate H from a knowledge of only the free currents. That's very useful in analyzing magnetic materials. First, though, let's talk for a second about a physical interpretation of these three fields, H, M, and B, because they arise from different origins. And just to be clear, let's go back to the original defining equation. We said, for reasons that really were mathematical ones, to simplify our equation, we said that H would be equal to 1 over mu naught B minus M. So if from this equation, if we solve for B, we write it the way that's probably easier to remember it, and this is what many books write. And of the two equations, I actually think that the second one really is the more useful one, because causally it gives us the right picture. It reminds us that B is the total field that arises from the sum of two different fields. So let's see what happens with a little cartoon that I can make up when we apply an external field to a magnetic material. Don't worry too much about what we call H. In Griffith's book, he just calls it H, and that's the way that I will refer to it. It really is a kind of a magnetic field, just with a slightly different dimension system. So let's imagine that we have a magnetic material and we put it inside a solenoid. So here, the gray box is the magnetic sample, and we put it in a solenoid so that now, in the solenoid, we're applying an external field H to this sample. And that's present inside the solenoid regardless of whether the sample is there. That is truly the external field, and it arises from the motion of the current in the loops around the solenoid. So what happens internally to the sample in response to this applied field is that there's a magnetization that's generated, right? Because either the rotation of the magnetic dipole moments, in the case of paramagnetism, or in the case of diamagnetism, the change in the speed of the orbital motion of the electrons that produces a change in the magnetization in the direction opposite to the applied field. One or both of those effects happens inside the sample. So that the net field inside the sample, which is what determines its properties, is actually the sum of those two fields. H represents the externally applied field. M represents what happens inside the sample in response to the applied field, and their sum, multiplied by mu0, gives us the net magnetic field B. Okay, so just as a note, I talked about paramagnetism and diamagnetism. Just be reminded that the direction of M inside the material depends on whether the material is dia or paramagnetic. So, for historical reasons, H and M have the same units, which you can see if you look at the equations at the top of the slide, while B differs by a factor of mu0. But all of them are still magnetic fields. They just have different origins. Remember that whenever we write down B, by convention, it's always the net magnetic field, due to whatever contributions there might be. So, what's the advantage of working with H? We'll wrap up just a little bit by talking about this because using it requires some examples, and I will show you some of those in class and have you work on some as well. But here's the advantage. If we know the magnetization M of a sample, and we know any free current density that we're passing through it, we can use the new form of Ampere's law if there's a high enough symmetry to find H. So then if we know H and we know M, we can get B directly, just by adding those two fields up and multiplying by mu0. So in this kind of a problem, if we have this kind of information about the magnetization and we can find H, we can get the magnetic field inside that material without any need to calculate the bound current densities at all. We could calculate them, but we don't need to. And so this approach simplifies the task of finding B inside the sample. We get it directly from knowing the magnetization. And you've got a couple of homework problems where you get a chance to do that. One final comment comparing magnetostatics and electrostatics, because in our definition of H and in developing a new version of Ampere's law, this ought to remind you of something that we did back in Chapter 4 with dielectric materials. H plays the same role in magnetostatics that the field D plays in electrostatics. So remember, using D allowed us to write down Gauss's law in terms of free charges alone, those charges that we control by pushing them around on, let's say, the plates of a parallel plate capacitor. So using Gauss's law in that form allowed us to solve for D first, which then in turn gave us E. All right, now in magnetostatics, it's very similar. Using H allows us to write Ampere's law in terms of just the free current alone. So it's easier to solve for H just from a knowledge of the free current, and if we do that first, we can get B. So the task is simplified in these alternate versions of Gauss's law and Ampere's law. and they make it particularly easy for us to study the properties of these fields inside of matter. But one final note, H is even more useful to an experimentalist in dealing with magnetic fields than D is in dealing with electric fields, for the simple reason that H is much easier to measure in the lab than D is. It's far easier in practice for the experimentalist to wind wires around a solenoid and control and measure the currents flowing through them, which are the things that produce H. It's much easier to do that than it is in the lab to control and measure the charges, the free charges that in turn produce the D field. In the lab, when we deal with electronic experiments, we usually control the potential difference, which does cause charge to flow, but we're not really controlling the charges directly. And so you'll never hear an experimentalist talking about the value of D. The experimentalist will talk about the voltage or maybe the electric field, whereas in the lab, when we deal with applying magnetic fields to samples, you'll often hear people talk about H as the applied field. So with this introduction, I hope that you'll take a look at the book and gain a little bit more insight from looking at examples, and we will work some out in class as well. That's where I'll see you.